Hey guys, this video is going to be about intermolecular forces. So intermolecular forces are forces of attraction, they can also be repulsion, that exist between two separate molecules. When I say separate molecules, that's what's usually looked at on an AP test. It's actually all the time. But they can exist in a very, very, very large molecule where it would bend back on itself and be attracted to itself, but that's not what we're discussing here. So I will keep it to separate molecules. But just know in the future, if you go further and further into chemistry, you may see where it happens in one molecule. All right, so if the molecules are strongly attracted to each other, you can see how it would affect a lot of properties of that substance. And the first one that's usually asked about is boiling point or melting point. So if you have two separate molecules, and I'm just going to draw them as circles here, and they're strongly attracted to each other, and let's say this is solid form, so this is an intermolecular force here, the green dots, then it would take quite a bit of heat to separate them and turn them into a liquid to where they're further apart. Same thing can be said as a liquid. It would take a large amount of heat to completely overcome the intermolecular forces to turn it into a gas. When we boil something, we have to completely overcome all of the intermolecular forces. So intermolecular forces are IMFs. So none can exist then. So that's why a lot of the time with boiling, or if you've seen a heat curve, right, where you've seen this curve, where this is temperature, and then down here is energy. So we have solid, liquid, gas, and then right here is the act of melting, and right here is the act of vaporization. This is usually much bigger because we have to overcome all of the intermolecular forces. So you have to put in a lot more energy there in order to overcome those forces and turn it into a gas. All right, so vapor pressure of a liquid. Now vapor pressure is something that we don't talk about that much in AP Chem. It should have been mentioned a little bit in pre-AP, but if I have a container of water, so this is liquid water, some of those water molecules, a few of them, will go into the vapor phase. And so they leave the surface of the water, and this is a closed container, and turn into gas. If the intermolecular forces are great with something, then less of those molecules are able to escape into the vapor phase because they're really attracted to each other in the liquid phase. So this actually gets reduced. Surface tension, it will increase. I think that's self-explanatory. You've all seen water bead up, and that's because the surface tension is increased. And viscosity increases. Viscosity is resistance to flow, so things flow slower, or things can't flow through them as easily. So if you think about something like Karo syrup or corn syrup, if you were to put a marble in a tube of that, it would flow very, very slow through that tube because it's very viscous. All right, those molecules are really attracted to each other. All right, and the phase of substances at a particular temperature is also affected. If it's a solid at room temperature normally, then it is very, very, very attracted to each other as compared to a liquid or a gas at room temperature. So the more intermolecular forces that they have, the more attracted they'll be to each other, and it can affect the phase that it exists in. So the first intermolecular force that we're going to talk about is ionic bonds. Now everybody knows what an ionic bond is, an attraction between a cation and an anion, and the first one is magnesium ion and the oxide ion, reversing that against sodium and chloride. So which of the following has the highest melting point? Now when we melt something like magnesium oxide, we melt it, it's going to turn into magnesium ions that are liquid and oxide ions that are liquid. That means that the attraction here between these two is an intermolecular force, and it's not like a real bond, because if we look at H2O solid, which is ice, and we melt it, it turns into H2O liquid. So it's a different kind of force that's existing between these two ions than there would be existing between the solid molecules of water. All right, so we can look at Coulomb's law to decide. So when you see a question that says highest melting point, what it's really asking you is which one of these ions are attracted to each other more. So we're going to use Coulomb's law to show which one of these is going to have a higher attraction, because whichever one has a higher attraction is going to have a higher melting point. So remember, Coulomb's law is force is equal to a constant times the absolute value of Q1 times Q2 over the distance squared, where Q1 and Q2 are charges. So those are the charges of the ions. And so since magnesium and oxide have a +2 and a -2, it is actually going to have a higher melting point there as compared to sodium and chloride with only a +1 and a -1. And the next question asks which one has the highest ionic attraction. We're using magnesium ions again with oxide versus calcium ions. And magnesium here is much smaller than calcium. Calcium is much bigger. So since it's smaller, it can get closer. And if it can get closer to oxygen, then that means this value will go down. If the denominator goes down, then that makes the overall fraction get larger. So that means that this one, again, will have a higher ionic attraction than calcium oxide. All right, an ion-dipole attraction is when a dissolved ion is attracted to the end of a polar molecule of opposite charge or opposite partial charge. So if we look at what happens to sodium chloride when we dissolve it in water, we have sodium chloride, and then we dissolve it in water, and they dissociate. So now we have the sodium ions and these chloride ions floating around in solution, and so sodium is positively charged, and if we look at what happens with a water molecule, water is polar, and so there will be a force of attraction between the negative end of the water molecule and the positive end of the water molecule will be attracted to the negative chloride. So I'm going to draw these in real quick and then I'll talk about it. All right, so as you can see, the negative end of the polar water molecule is attracted to the sodium ion, while the positive end of the water molecule is attracted to the chloride ion. And so the little green dots are the ion-dipole attraction. So what you have to have for ion-dipole to exist is you have to have an ion and you have to have a polar molecule. That's ion-dipole. All right, so there's lots of cool things that this affects, but we're really not going to go into it. I just want you to be able to identify it, and I also want you to be able to know that this would happen with any polar molecule and with any set of ions. Also, when you draw these ions, if you ever have to draw them, make sure that you draw them, if this was magnesium chloride, that you would draw magnesium ions and 2 chloride ions, and that you make sure that there's 2 chloride ions drawn with the same amount of water molecules attached to it, and then twice as many water molecules attached to the magnesium. All right, so that brings us to hydrogen bonding, and hydrogen bonding is not a bond. None of these are real bonds. They're all intermolecular forces. So we're going to use water as an example here, so I'm just going to draw a water molecule really quick, and we're going to look at what's happening within the molecule first. So this is a covalent bond, and what that means is these electrons in that bond are being shared between oxygen and hydrogen. So hydrogen is just a proton with one little bitty electron. It brings its only electron to that bond. And oxygen is so very electronegative that it takes the electron density that's in this bond, steals it away, so that it's hanging out more up here, close to oxygen, away from hydrogen. And what that basically does is it leaves that hydrogen very, very positive. So it's kind of like a bald proton sitting out here. all right? It hasn't taken it completely away, so it's not a full positive charge, but it's taken it away enough to where there's a lot of positive charge out there, all right? So this is happening on both sides, and because of that, this is a special type of polar molecule that forms a hydrogen bond, what we call a hydrogen bond. And so I'm going to draw another water molecule over here, and then one down here. All right, and then the hydrogen bond forms right here. So this partially positive hydrogen is attracted to this lone pair on the oxygen. And the same thing will happen for all of these. So water can form these really tough, what we call hydrogen bonds. Even though they're not real bonds, they're forces of attraction between two molecules. So you can see the difference between a bond and a hydrogen bond. We usually draw hydrogen bonds or any type of intermolecular forces as dots or dashes, whereas a bond is going to be a line. All right, and now I have another example of hydrogen bond that I think is important to show you. It's almost on every single AP test, so it's got to be important, right? And this is what happens in DNA. So these are the base pairs in a strand of DNA. So you know how you have DNA is the double helix, right? And you have these base pairs that exist. So there's a sugar phosphate backbone, and you have these base pairs that come out. I'm going to draw them as little green dots and cross over and hold those two separate strands together. And there's a force of attraction that occurs between them, and that force of attraction is actually a hydrogen bond. So those hydrogen bonds are not real bonds, and we can look right here. So there's a nitrogen, right? And it says that the hydrogen has to be directly covalently bonded to nitrogen, oxygen, or fluorine. So that has to be electronegative enough to pull enough electron density away from hydrogen to cause it to be positively charged enough for hydrogen bonding to occur. This hydrogen is covalently bonded to nitrogen. And then across the way, so this is cytosine. You know that in DNA, C has to go to G and T has to go to A. So A to T, C to G. Across the way, we have this oxygen that has those lone pairs on it. And so it's attracted to those. And it forms a hydrogen bond. And the same thing happens here. The same thing happens here. And T to A fit together perfectly. Now, if I was to put T to, let's say, G, we would have this poking out right at that. And so it wouldn't fit. So that's why DNA works the way it does. And not only that, but if these were actual real bonds, then when we split the two strands of DNA to replicate it, which we have to do to make new cells, if they were real bonds, all of these bonds in here would break. They would all fall apart and break. So when we replicate DNA, we sever these hydrogen bonds. We don't sever real bonds, and that's why it works so well. All right, dipole-dipole attraction is next. So it's an attraction between polar molecules. So it doesn't have to be, it's not a hydrogen bond, but it's just a polar molecule. So I'm just going to use HCl. So chlorine is not one of those atoms. It's not nitrogen, oxygen, or fluorine that forms hydrogen bonds. So if we look here, this is polar going towards chlorine because chlorine is the more electronegative atom. And so that means that this side would be partially negative, and it would leave this side partially positive. So another HCl sitting next to it would be attracted right here. So this would be a dipole-dipole interaction. All right, London dispersion forces. This is the hardest one to understand, but it's the easiest one to recognize because it's in every single molecule. All right, so if you can imagine that you have a molecule and all of the electrons ended up on one side, that would cause a partial negative charge on that one side and leave the other side of the molecule partially positive. So we call those instantaneous dipoles. That makes the molecule that sits next to it get a dipole, and then the two molecules are attracted to each other. If you look at the halogens, so if we have F2, Cl2, Br2, and I2, and if you know anything about these, this is a gas at room temperature, This is a gas at room temperature. This is a liquid at room temperature, and this one is a solid, which means that the attractive forces are increasing as we go down the periodic table. All right, and it's just a fluorine to fluorine, chlorine to chlorine, bromine to bromine, and iodine to iodine. And so those are not polar bonds. There's nothing polar about them. They're both the same on both sides. And if we look at how many electrons these have, well, a fluorine has 9, and there's 2 of them, so that's 18. Fluorine has 17, and there's 2 of them, so that's 34. Bromine has 35, and there's 2 of them, so that's 70. And iodine has 53, and there's 2 of them, so that's 106 electrons. So those are the total number of electrons. So this one has more electrons, therefore it can get a bigger dipole. There's also something called polarizability. And I always think of polarizability as squishy. So if you think of this like a Nerf ball or a sponge ball, one of those spongy balls, maybe bromine is more like a Nerf ball, and fluorine is like a marble. So they get more squishy. And if they're more squishy, they have more space, and so the electrons can really go to one end of that molecule way easier and cause a bigger discrepancy in charge across the molecule and a bigger force of attraction. So that's something to think about. But that's why this has so many more electrons that it's a solid. So if you're just comparing nonpolar molecules, you can look at the mass to determine which one is going to have a greater force of attraction, but a lot of the time we refer to it as polarizability. Also, if you have something that's straight chain versus branched, okay, both of those have the exact same formula, but this one is going to have a higher force of attraction, and I call them LDFs, not IMFs, but LDFs, because it's not branched. So they can actually get closer together than something that's branched. So branched molecules have lower attraction. Here's the example. We're going to look at these molecules and determine which intermolecular forces are present and put an order of increasing boiling point. So this first one, we have SO3, and so it can be drawn like that, or it can be drawn like this if you're looking at formal charges, so we get rid of those lone pairs and make them all double bonds. Either case, it's the same shape, it's trigonal planar. And so this is a nonpolar molecule, so it would only have LDFs. All right, and then we have, this is acetone, and acetone is polar towards oxygen. There is no hydrogen bonding here because there is not a hydrogen that's bonded directly to a nitrogen, oxygen, or fluorine, but it is polar. So it's going to have dipole-dipole interaction, and it's also going to have LDFs because everything has LDFs. All right, and then next we have carbon to chlorine bond, which is going to be polar bond. But since they're all polar, they all cancel out. And so therefore, this is only going to have LDFs. All right, and then down here we've got acetic acid, and it is going to have hydrogen bonding. Okay, but this right here is a covalent bond. So this hydrogen has the capability of hydrogen bonding. Let's put it like that. All right, and it also is going to have dipole-dipole because it's polar, and it will also have LDFs. All right, and then down here we've got nitrogen to hydrogen, which is going to be, so both of these can hydrogen bond, and so it will also have dipole-dipole and LDF. So anything that has hydrogen bonding also has dipole-dipole. Methane, CH4, this is going to have only LDFs. We consider C to H bonds to be nonpolar. Helium will only have LDFs, and then this is polar, so this is going to have dipole-dipole, LDFs. So remember that you have to have a hydrogen. For hydrogen bonding, it has to be directly bonded to nitrogen, oxygen, or fluorine. All right, and then if I look at these and I want to put them in order of increasing boiling point, then I need to look at their masses. So I'm just going to quickly calculate the masses. So this would be 35 and 70, 140. So this is 152. Helium is 4. Methane is 16. This would be 80. All right, so that means that the ones with only LDFs will probably have the lowest. So helium would come first, and then we would have methane, and then we would have SO3 and carbon tetrachloride. All right, and then we're going to go to the ones that have dipole-dipole and LDFs. And since they both have dipole-dipole, I would assume that this one would have a higher boiling point. One, because its LDFs would be larger, and two, because that bond is way more polar than the bond that's in the CH3Cl. So I'm going to put CH3Cl down here, and then I'm going to put the acetone. And then we're going to look at the ones that have hydrogen bonding. All right, now although this methylamine down here in the left-hand corner may have more hydrogens to hydrogen bond, the nitrogen to hydrogen bond is less polar. Not only that, but we've got two oxygens here in this one that's pulling the electron density away. So I would say that the methylamine is going to have a lower boiling point than the acetic acid.